Chapter 7. This chapter is about spin locks and contention. You can classify processors by how they manage data and instruction streams. A single instruction, single data stream architecture is just a uniprocessor. A single instruction, multiple data stream is a vector machine. These were popular for a while in the past, and then they fell out of favor in place of multiple instruction, multiple data streams, ArgSpace. But current machines combine SIMD and MIMD. There are two basic kinds of MIMD architectures. In a shared bus architecture, processors and memory are connected by a shared broadcast medium called a bus, like a tiny Ethernet. Both the processors and the memory controller can broadcast on the bus. Only one processor or memory can broadcast on the bus at a time, but all processors and memory can listen. Bus-based architectures are the most common today because they are easy to build. The principal things that affect performance are: 1. Contention for memory. Not all the processors can usually get at the same memory location at the same time, and if they try, they will have to queue up. 2. Contention for the communication medium. If everyone wants to communicate at the same time or to the same processor, then the processors will have to wait for one another. Finally, there is growing communication latency, the time it takes for a processor to communicate with another processor. At one time, CPUs were slower than main memory. Around the 60s, that changed. Increasingly, CPUs have become faster than memory. The result is that CPUs become starved for data. Contention makes this problem worse. As a result, there are limits to shared memory architecture. NUMA, or non-uniform memory architecture, was invented in the 90s to make this situation better. In NUMA, each processor is closer to a different part of memory. Each CPU is faster when accessing its own memory than that of another CPU. Clusters distribute the memory even more, and CPUs can only communicate by sending explicit messages. Because of this, clusters typically have high-speed networks called interconnects. RDMA, or Remote Direct Memory Access, allows one CPU to take control of the bus on another CPU through the interconnect, even performing atomic instructions there. Almost any mutual exclusion protocol poses the question, what do you do if you can't acquire the lock? There are two alternatives. If you keep trying, the lock is called a spin lock, and repeatedly testing the lock is called spinning or busy waiting. We will use these terms interchangeably. The filter and bakery algorithms are spin locks. Spinning is sensible when you expect the lock delay to be short. For obvious reasons, spinning makes sense only on multiprocessors. The alternative is to suspend yourself and ask the operating system scheduler to schedule another thread on your processor, which is sometimes called blocking. Java's built-in synchronization is blocking. Because switching from one thread to another is expensive, blocking makes sense only if you expect the lock delay to be long. Many operating systems mix both strategies, spinning for a short time and then blocking. Both spinning and blocking are important techniques. In this lecture, we turn our attention to locks that use spinning. With spin locks, synchronization usually looks like this. Some set of threads contend for the lock. One of them acquires it, and the others spin. The winner enters the critical section, does its job, and releases the lock on exit. Contention occurs when multiple locks try to acquire a lock at the same time. High contention means there are many such threads. Low contention means the opposite. Now let's take a look at test and set locks. The test and set machine instruction atomically stores true in a word, and then returns that word's previous value, swapping the value of true for the word's current value. You can reset the word just by writing false to it. Note that in Java, TAS is called get and set. We use test and set and get and set interchangeably. The test and set machine instruction with consensus number 2 was the principal synchronization instruction provided by many early multiprocessors. Here we're going to build one, an atomic Boolean class, which is provided as part of Java's standard library of atomic primitives. You can think of this object as a box holding a Boolean value. The get and set method swaps a Boolean value with the current contents of the box. At first glance, the atomic Boolean class seems ideal for implementing a spin lock. If we call get and set true, then we have a test and set. So how do we build a test and set lock? The basic idea is that if the lock is free, the atomic Boolean will be holding a false. If the lock is taken, it will be holding a true. So we acquire the lock by calling TAS, and if the result is false, then you win, you have the lock. If the result is true, you don't have the lock, and you have to keep trying. You can release the lock if you have it by writing false. So here's what it looks like in more detail. First, we initialize the state of the lock to false. Next, we keep trying to set the state to, we keep trying a get and set until we get a false. Finally, when we want to unlock, we set the state to false. Now let's think about space complexity. The TAS or spin lock has a small footprint. What does this mean? It means that it uses only one word of space, as opposed to a Peterson or Bakery lock, which will use order n space. How did we overcome this limitation? By using an RMW operation. So let's do an experiment. So here's a good point to pause and ask for questions, I think. Does anybody have a question on how TAS works? Christopher?
No question.
Take n threads and have them collectively acquire a lock, increment the counter, and release the lock. Have them do it, say, 1,000,000 times. Before we try to look at any curves, let's try to reason about how long it should take. Ideally, the curve should stay flat. Why? Because we have a sequential bottleneck. So no matter how many threads we add in running in parallel, we will not get any speed up. Remember Amdahl's law. So this is what we expect. The curve
Somebody's
for the TAS
trying to join.
lock looks like this. In fact, if you do the experiment, you have to give up because it takes so long beyond a certain number of processors. What's happening? Let's try this again. Let's try a slightly different approach. Instead of repeatedly trying to test and set the lock, let's split the locking method into two phases. In the first phase, the lurking phase, we wait until the lock looks like it's free, and then when it's free, we pounce, attempting to acquire the lock by a call to test and set. If we win, we're in. If we lose, we go back to lurking. Here is what the code looks like. First, we spin on the value, repeatedly reading it until it looks like the lock is free. We don't try to modify it, we just read. As soon as it looks like the lock is free, we call test and set to try and acquire it. If we are first and we succeed, the lock method returns, and otherwise, if someone else got there before us, we go back to lurking to repeatedly rereading the variable. Now let's try our experiment again. The difference is dramatic. The TTAS lock performs much better than the TAS lock, but still much worse than we expected from an ideal lock. So both TAS and TTAS do the same thing in our model, except that TTAS performs much better than TAS. Neither approach, however, is ideal. We are going to do yet another review of the multiprocessor architecture. The processors share a memory that has a high latency, say 50 to 100 cycles, to read or write a value. This means that while you are waiting for the memory to respond, you can execute that many instructions. Processors communicate with the memory and with one another over a shared bus. The bus is a broadcast medium, meaning that only one processor at a time can send a message, although everyone can passively listen. Each processor has a cache, a small, high-speed memory where the processor keeps data likely to be of interest. A cache typically requires 1 or 2 machine cycles, while a memory access typically requires tens of machine cycles. Technology trends are making this contrast more extreme. Although both processor cycle times and memory access times are becoming faster, the cycle times are improving faster than the memory access times, so cache performance is critical to the overall performance of a multiprocessor architecture. If the processor doesn't find what it wants in its cache, then we have a cache miss, which is very time-consuming. How a well-synchronized protocol or concurrent algorithm performs is largely determined by its cache behavior, how many hits and how many misses. Here is something that can happen when a processor issues a load request. It broadcasts a message asking for the data it needs. Notice that while it is broadcasting, no one else can use the bus. In this case, the memory responds to the request, but also over the bus. Now suppose another processor issues a load request for the same data. It broadcasts its request over the bus. This time, however, the request is picked up by the first processor, which has the data in its cache. Usually, when a processor has the data cached, it, rather than the memory, will respond to the load request. The processor puts the data on the bus. Now both processors have the same data cached. Now what happens if the red processor decides to modify the cached data? It changes the copy in its cache from blue to white. The data stored on the red processor's cache is different from the data cached here and the data in main memory. The problem of keeping track of multiple copies of the same data is called cache coherence, and the ways to fix it are called cache coherence protocols. A write-back coherence protocol sends out an invalidation message when the value is first modified, instructing the other processors to discard that value from their caches. Once the processor has invalidated the other cached values, it can make subsequent modifications without further bus traffic. A value that has been modified in the cache but not written back is called dirty. If the processor needs to use the cache for another value, however, it must remember to write back any dirty values. Instead, we keep track of each cache's state as follows. If the cache is invalid, then its contents are meaningless. If it is valid, then the processor can read the value, but does not have permission to write it because it may be cached somewhere else. If the value is dirty, then the processor has modified the value, and it must be written back before that cache can be reused. Let's rewind back to the moment when the red processor updated its cached data. It broadcasts an invalidation message warning the other processors to invalidate or discard their cached copies of that data. When the other processors hear the invalidation message, they set their caches to the invalid state. From this point on, the red processor can update that data value without causing any bus traffic, because it knows that it has the only cached copy. This is much more efficient than a write-through cache, because it produces much less bus traffic. Finally, there is no need to update memory until the processor wants to use that cache for something else. Any other processor that asks for the data will get it from the red processor. If another processor wants the data, it asks for it over the bus, and the owner responds by sending the data over. Now both have the same data, and reading is okay, but not writing. Now consider the behavior of the TTAS lock algorithm while the lock is held by thread A. The first time thread B reads the lock, it takes a cache miss, forcing B to block while the value is loaded into B's cache. As long as A holds the lock, B repeatedly rereads the value.
Sorry,
Each time-
I meant to pause just a little bit before this. Does anybody have any questions about all this information about the bus and cache coherency? All right. Again, please feel free to interrupt the video at any time and ask a question.
And B hits in its cache, finding the desired value. B thus produces no traffic and does not slow down the other thread's memory accesses. Moreover, a thread that releases a lock is not delayed by threads spinning on that lock. While the lock is held, all the contenders spin in their caches, rereading cache data without causing any bus traffic. Things deteriorate, however, when the lock is released. The lock holder releases the lock by writing false to the lock variable, which immediately invalidates the spinner's cached copies. Each one takes a cache miss and rereads the new value. And they all, more or less simultaneously, call test and set to acquire the lock. The first to succeed invalidates the others, who must then reread the value, causing a storm of bus traffic. So we now understand why the TTAS lock performs much better than the TAS lock, but still much worse than an ideal lock. Another approach is to introduce a delay. If the lock looks free, but you can't get it, then instead of trying again right away, it makes sense to back off a little and let things calm down. For how long should the thread back off before retrying? A good rule of thumb is that the larger the number of unsuccessful tries, the higher the likely contention, and the longer the thread should back off. Here is a simple approach. Whenever the thread sees the lock has become free, but fails to acquire it, it backs off before retrying. To ensure that concurrent conflicting threads do not fall into lockstep, all trying to acquire the lock at the same time, the thread backs off for a random duration. Each time the thread tries and fails to get the lock, it doubles the expected time it backs off, up to a fixed maximum. Here is the code for an exponential backoff lock. The constant min delay indicates the initial shortest limit. It makes no sense for the thread to back off for too short a duration. As in the TTAS algorithm, the thread spins, testing the lock until the lock appears to be free. Then the thread tries to acquire the lock. If it fails, then it computes a random delay between 0 and the current limit, and then sleeps for that delay before retrying. It doubles the limit for the next backoff up to the max delay. It is important to note that the thread backs off only when it fails to acquire a lock that it had immediately before observed to be free. Observing that the lock is held by another thread says nothing about the level of contention. The graph shows that the backoff lock outperforms the TTAS lock, though it is far from the ideal curve, which is flat. The slope of the backoff curve varies greatly from one machine to another, but it is invariably better than that of a TTAS lock. The backoff lock is easy to implement and typically performs significantly better than TTAS lock on many architectures. Unfortunately, its performance is sensitive to the choice of minimum and maximum delay constants. To deploy this lock on a particular architecture, it is easy to experiment with different values and then choose the ones that work best. Experience shows, however, that these optimal values are sensitive to the number of processors and their speed, so it is not easy to tune the backoff lock class to be portable across a range of different machines. We now explore a different approach to implementing spin locks, one that is a little more complicated than backoff locks, but inherently more portable. One can overcome these drawbacks by having threads form a line, or a queue. In a queue, each thread can learn if its turn has arrived by checking whether its predecessor has been served. Invalidation traffic is reduced by having each thread spin on a different location. A queue also allows for better utilization of the critical section, since there is no need to guess when to attempt to access it. Each thread is notified directly by its predecessor in the queue. Finally, a queue provides first come, first served fairness, the same high level of fairness achieved by the bakery algorithm. We now explore different ways to implement queue locks, a family of locking algorithms that exploit these insights. Here is the Anderson queue lock, a simple array-based queue lock. To acquire the lock, each thread atomically increments the tail field. Call the resulting value the thread slot. If the value of that slot is true, the thread acquires the lock. When the Anderson lock is initialized, slot 0 is set to true. The next slot will be set to true when we release the lock. If the flag at slot is true, then the thread acquires the lock. If it is false, the thread spins until the flag at its slot becomes true. Here, another thread wants to acquire the lock. It applies get an increment to the next pointer. It advances the next pointer to acquire its own slot. Then it spins until the flag variable at that slot becomes true. The first thread now releases the lock by setting the next slot to true. The second thread notices the change and enters its critical section. Here is what the code looks like. We have one flag per thread. This means we have to know how many threads there are. The next field tells us which flag to use. Each thread has a thread local variable that keeps track of its slot. Here is the code for the lock and the unlock methods. First, claim a slot by atomically incrementing the next field. Next, wait until my predecessor has released the lock. Reset my slot to false so that it can be used for the next time around. To release the lock, set the slot after mine to true, being careful to wrap around. Is spinning really local if multiple threads bits sit in the same cache line? No. False sharing occurs when a thread spinning on one bit incurs an invalidation of the line it is spinning on, even though the actual bit it is interested in has not changed. Does everyone understand the concept of false sharing? Does anyone not understand it?
No.
I'm sorry, what? Yeah, so the concept of false sharing, when data is read from the cache, right, it's not read just a word at a time. It grabs a whole bunch of data that's contiguous on the assumption that you're processing a loop or an array and that you're working on one thing after another. That way the data is ready by the time you go to use it, right? And so when cache is read in, it's read in as a big chunk. Now, if we read in this array of flags as one big chunk from cache and we invalidate it together and we mark it dirty as one object together, then we lose the thing that we're trying to achieve with this array of flags. Does that make sense?
Yeah.
Okay. To avoid false sharing, each bit needs to sit in a separate cache line. The Anderson queue lock improves on backoff locks because it reduces invalidations to a minimum and schedules access to the critical section tightly, minimizing the interval between when a lock is freed by one thread and when it is acquired by another. There is also a theoretical benefit. Unlike the TTAS and backoff lock, this algorithm guarantees that there is no lockout. In fact, it provides first come, first served fairness, which we actually lose in TTAS and TTAS with backoff. So here's what's good about the Anderson queue lock. It's the first truly scalable lock. It's simple, easy to implement. It takes us back to FIFO order, like bakery. But the Anderson lock has several disadvantages. First, it is not space efficient. It requires knowing a bound n on the maximum number of concurrent threads, and it allocates an array of that size per lock. Thus, L locks will require order log ln space, even if a thread accesses only one lock at a given time. Second, the lock is poorly suited for uncached architectures, since any thread may end up spinning on any array location, and in the absence of caches, spinning on a remote location may be very expensive. Finally, even with caching, one must use some form of padding to avoid false sharing, which increases the space complexity further. The CLH-Q lock by Travis Craig, Eric Hagerston, and Anders Landon. Sorry, any questions so far? Much more space efficient, since it incurs a small, constant size overhead per thread. This algorithm records each thread's status in a QNode object, which has a Boolean locked field. If that field is true, then the corresponding thread either has acquired the lock or is waiting for the lock. If that field is false, then the thread has released the lock. The lock itself is represented as a virtual linked list of QNode objects. We use the term virtual because the list is implicit. Each thread points to its predecessor through a thread local pred variable. The public tail variable points to the last node in the queue. So here is the initial state. We have a tail node pointing to a queue node, which is false. That means the lock is free. Initially, some thread wants a lock, so it attempts to acquire it. To acquire the lock, the thread sets the lock field of its queue node to true, meaning that the lock thread is not ready to release the lock. The thread applies swap to the tail to make its own node the tail of the queue, simultaneously acquiring a reference to its predecessor's queue node. Because it sees that its predecessor's queue node is false, this thread now has the lock. Another thread that wants the lock does the same sequence of steps. Notice that the list is ordered implicitly. There are no real pointers between the nodes. The thread then spins on the predecessor's queue node until the predecessor releases the lock. The thread actually spins on a cached copy of purple's node, which is very efficient in terms of interconnect traffic. In fact, in some coherence protocols for shared memory, this might not even be updated at all. When a thread acquires a lock, it can reuse its predecessor's queue node as its new node for future lock accesses. Note that it can do so since, at this point, the thread predecessor's queue node will no longer be used by the predecessor, and the thread's old queue node is pointed to either by the thread's successor or by the tail. The reuse of queue nodes means that for L locks, if each thread accesses at most one lock at a time, we only need order L plus n space, as compared with order L times n for the A lock. Here is what the node looks like as a Java object. If the locked field is true, the lock has not yet been released. It may also not have been acquired. Here is the code for the lock. Here we declare the tail variable. Here we declare the mynode thread local variable. Swapping the tail pointer with my node is the first step in acquiring the lock. We now spin on the predecessor's locked field. Here is the unlock method. We notify the successor that we are done with the lock, and we recycle the predecessor's node. If we don't do this, we could set our own flag to true again before the next thread sees the lock. That would lead to deadlock. The safe thing to do is to think of ownership passing to the next node as soon as false is written to the locked field. Like the A-lock, this algorithm has each thread spin on a distinct location. When one thread releases its lock, it invalidates its successor's cache only, and does not invalidate any other thread's cache. It does so with lower space overhead, and importantly, without requiring prior knowledge of the number of threads. The principal disadvantage of this lock algorithm is that it performs poorly on cacherless NUMA architectures. Each thread spins waiting for its predecessor's nodes to become false. If this memory location is remote, then performance will suffer. On cache-coherent architectures, however, this approach should work well. Spinning on local memory is fast. Spinning on remote memory is slow. Each thread spins on predecessor's memory in the CLH lock, and this could be far away. The MCS lock is another kind of queue lock that ensures that processes always spin on a fixed location, so this one works well for cacherless architectures. Like the CLH lock, it uses only a small fixed size overhead per thread. Here too, the lock is represented as a linked list of queue nodes, where each queue node represents either a lock holder or a thread waiting to acquire the lock. Unlike the CLH lock, the list is explicit, not virtual. Initially, the tail points to null. To acquire the lock, a thread places its own queue node at the tail using swap. At this point, the swap is completed, and the tail points to the purple thread's queue node. If the predecessor node is null, we have the lock. Another thread now attempts to acquire the lock. It swaps the tail pointer. For the red thread, the predecessor is not null. The red sets its waiting flag to true and assigns the predecessor's next pointer. The red thread now spins on its own node, waiting for the flag to be unset. Purple notifies red that it has released the lock. Red sees the state change and gets the lock. Here is what a node looks like for the MCS lock. Here is how the algorithm looks. To acquire a lock, we allocate a queue node. We swap our node into the tail. If our predecessor is not null, we set the locked field to true and set the next pointer. We now spin on the locked field. Here is the unlock method. First, check if next is set. If it's not, attempt to set the tail pointer. If we succeed, then no one is waiting for the lock. If setting the tail failed, someone is attempting to acquire the lock. Wait for the next field to be set. Notify the successor that they can have the lock. Here's a graphical depiction of that code. Purple decides to release the lock. Purple's next field is null. However, purple sees that the tail does not point to its own queue node. Purple knows to wait for its next pointer to be set. Red updates its field to true and sets purple's next pointer. Red spins on its locked field. Purple sees that its next pointer is set and notifies red that it can have the lock. Red has the lock. In this lecture, we saw a variety of spin locks that vary in characteristics and performance. Such a variety is useful because no single algorithm is ideal for all applications. For some applications, complex algorithms work best, and for others, simple algorithms are preferable. The best choice usually depends on the specific aspects of the application and the target architecture. Thank you for listening. Chapter 7. Okay, so that was the recorded portion, pre-recorded portion of the lecture. I want to do a few more little things, but before I go on, I want to get some impressions. Do you like it better with the pre-recorded lecture, or do you like it better when I wing it? Any thoughts? Who prefers winging it? Who likes the pre-recorded?
I think it's probably the winging it is nice because the pace isn't sort of preset, right? So if there are questions, it does feel easier to cut in while you're doing it live, right? But the pre-recorded version I think is nice because it does, I mean, it keeps pace, right? But yeah, it's harder to cut in with questions.
I could just record more places to cut in. I could just, stop and while I'm doing the pre-recorded one in various places and just pause. Maybe I should do that. Maybe that would give me the best of both worlds. I don't know. All right, one of the things I'd like to show you is that I did, I've coded these algorithms and I ran them just to see how well they did. And I did pick kind of some arbitrary numbers, but you have to pick some arbitrary numbers to run a test. And you can sort of see what happened here. I can just rerun it, but so this is running on a machine that has a NUMA architecture, and it has 40 cores. So I picked the number of threads to be 40 to match the machine. And then I just sort of picked arbitrarily the other values such that I got reasonable times. So this first lock took, for the exercise I gave it, took 8.5 seconds roughly. The TTAS lock was an enormous improvement on that, as you can see, from 8.5 down to 1.3. The back-off lock, I played with a couple of different values for the min and max, and generally speaking, at least on this machine, the back-off lock performed worse than the TTAS lock for the particular parameters that I chose for the experiment that I designed. The A-lock did slightly worse in this particular run, it looks like. And okay, so this S was a variant of the A-lock, but I used classes instead of Booleans. The CLH lock was slower. Slower than the A-lock and slower than the TTAS. But the MCS lock succeeded in beating everyone. So let me just sort of run this again. Now, one of the interesting things was when I ran these tests on my laptop, which only has 3 cores and does not employ NUMA architecture, everything performed roughly the same as the TAS lock. Nothing really provided any advantage. So, you have to be careful with these things. You have to, and you notice if I just run it at a different time, I get different results, right? Everything takes slightly different than it did the last time I ran it. So the TAS was about 8 before, and this time it's 12, okay? And my TTAS was 1.4, and my backoff provided no benefit, but this time it did. So because there is a non-determinacy in parallel applications, this kind of thing is expected. and it makes figuring out which is the best that much more difficult. In addition to the architectural considerations for which is the best, there are also applications. It depends on how you're using the locks. So figuring out what the best performing lock is for your particular needs is not a trivial thing. I mean, it's something that you have to really work at, and you might have to figure out on each new machine you go to which is the best. Let me just play with this code a little bit. Number of threads. Let's not try to use everything on the whole machine. That might be creating some strain. Let's push that down to 30. See how we do with that. Now, you notice that with this particular run and these particular parameters, the A-lock did best. Let me raise that to 7. Just give it a little more work to do. Okay, so here again, you see some different results. So again, depending on the level of parallelism of my application and my machine and so on, different locks come out on top. Are there any questions? So, right.
Huh?
Do you perfectly understand the CLH lock?
No.
Then why don't you have a question?
I mean, usually I don't understand most topics until I watch the lectures a few times.
Okay. But what I'm trying to do, right? What I would like for to happen here is while we're all together, right? What is the most fuzzy thing in your minds? What is the thing in this lecture that made the least amount of sense?
I mean, I'm not sure. It was kind of a lot of material.
Right. But if you were to pick something, if you just say, this is a thing that just didn't make sense to me, what is a thing? What's the first thing that comes to your mind?
I suppose the last block before you talked about NUMA architecture.
The last lock before I talked about NUMA architecture, that would be the CLH lock.
Oh, well, that one.
So the CLH and MCS lock are things that you really have to stare at for a while before they fully make sense to you. And I think it really helps to code them, right? I know that it helps me to understand an algorithm if I actually code it and I try to make sure it works the way I think it does, because very often it doesn't. And in this case, one of the things I discovered in the process of coding it up is they don't mark these fields as static in the sample codes that they give for the CLH lock, but I found that they work perfectly fine with static, and that cuts down the amount of memory the algorithm uses by a lot. Okay, so the lock method, right? We have this thing called a Q node, and a Q node just has a single field on it called locked. All right, so what I do is I get my Q node, and then I I set it to false because I need it to be false before, or I'm sorry, I set it to true because that means I want to obtain the lock. And then I do this get and set thing to put my lock into the tail so that anybody else who wants to get the lock has to get it from my Q node. All right. And then I keep track of who the predecessor is. The predecessor is going to be whatever was in the tail before I called get and set. And now what I'm going to do is I'm just going to spin on the predecessor's locked field, right? I want to know when that predecessor is done with the lock. And as soon as that is yielded, I'm going to go ahead. Now the unlock method, right? What I'm going to do is I'm going to get my node, my Q node. I'm going to set the locked field to false. Now, if there's somebody else waiting for a lock, they're going to be looking at this field and waiting for it to be false. They're going to be stuck in this loop here. And then once I'm done, I'm going to set my node to what the predecessor's node was. And that might seem a little confusing. You know, why am I doing that? Why am I just not keeping my node? But here's what could happen, right? I could set this locked field to false. And then I could go back into locked and set it back to true, and somebody else could be watching, and I could get into a really sticky situation there. So the basic plan is that once you've marked that locked false, you figure that node belongs to the next one who's looking at it, the one that's spinning here and waiting to see something, right? We don't know when they're going to see it, and we don't want to figure that out. So we just figure that node is theirs from now on. Does that make a little more sense now?
Yeah, this is the one that is most like a FIFO queue, right?
So the A lock, the CLH lock, and the MCS lock are all FIFO queues.
Yeah.
They all kind of work the same way. They all have a notion of who the predecessor is and who the next one is, right? So in the A lock, we do it with an array, and we just count over to the next one, and when the array can wrap around as well. But so that's how that works. But this one does it with pointers instead of having an explicit array of who and marking the, the next integer is the next one. We chase through a field. I mean, we chase through this get and set thing to know who our predecessor is. Anyway, the CLH and the MCS lock are kind of the are clearly the most difficult to understand here, right? So if I were to pull up the MCS lock code, okay, and I were to ask you, what's going to happen if I have an MCS lock and I call this tail.get and set, and I get a null back from the predecessor? What happens?
Nothing happens.
Okay, so nothing happens in the body of the lock field, and what does that mean?
Yeah, it successfully locks.
It successfully locks, right? If I get a null back, it successfully locks. Now, if I don't get a null back, right, then I mark this q.locked field as true. Okay, and then I set the next field. Okay, and then I wait for q dot locked to become false. Now, if I look at the unlock field, one of the things you have to ask yourself is, okay, so let's look at this tail that compare and set q node null. What this is going to do, right, is if the tail is still pointing to the current lock, it's going to try to set it to null. And if it succeeds, it's going to return. So let's pretend there's another thread, and that other thread is going to call its line 28 just before this compare and set. What's going to happen? Is the compare and set going to succeed or fail? Or could it do both?
Could you repeat the question, please?
Okay, so I have thread A is getting ready to call this line of code. But just before it does, thread B calls this line of code. What's going to happen with the compare and set? Is it going to succeed, fail, or can't you tell?
Can't tell.
Any other opinions? No other opinions. So notice compare and set, what it's going to do is it's going to try to say, it's going to say, I think that the tail contains the value q node, that is my node. I think the tail contains my node, and if it does, set it to null, otherwise fail, right? Now, on line 28, we have a different thread calling get and set with its q node, right? It's going to set that value to its q node, and it's going to get back whatever was there. So let me ask again, do you think this is going to succeed?
No, it should fail.
It should fail, right? If thread A first locked by setting thread A's q node into the tail, and then when it gets to here, just before it does the compare and set, if thread B comes in and changes the q node, then this is guaranteed to fail. Okay, and what that means is, because it failed, I know that just before this compare and set was called, or sometime while I was holding the lock, somebody came in there and replaced the tail with this get and set. And since somebody else, since it got changed from when I set it, that means that I have to set the q node dot next field. Now the q node, I mean, I have to set this locked field to false. Okay, but I know that in order to do that, I have to set the q node next field. I have to have access to q node dot next. But it might be the case that this other node that's attempting to lock it has not yet set the next field, right? It might not have gotten to this line of code yet. It might have executed this line, but not this line. And so I have a while loop here just to wait for that. So let me ask you this question. Is the unlock method on the MCS lock wait free?
No.
This is the MCS lock, right?
I'm sorry, the MCS lock. What did I say?
No, you said MCS. This is the MCS lock, right?
Yes. Right. And so, right, you're correct. The answer is no. This is not wait free. If you have a while loop like this where you're waiting for another thread to do something, you are not wait free in any sense. Okay.
So because this is not wait free, you get the benefit here of having first come first served priority, but where is the time benefit showing up if you're spinning anyway, right? Like what's the benefit of this over a spin lock when it comes to that waiting overhead?
So the issue that we've been dealing with here is the cache, right? And the problem is with a spin lock, where all the threads are trying to access the same memory. And every time you invoke a get and set or a compare and set on that location, you're sending an invalidation across the cache, right?
Even on just the read?
If you're just doing a read, you're not invalidating. That's why the TTAS lock is a benefit over the TAS lock, because the TAS lock is always writing, right?
Right, okay. So then,
okay.
so
So
what's the benefit here over TTAS then?
the benefit over TTAS, right, is these Q nodes are only being, each individual Q node is only visible to two threads, right? There's the one that locked it and the one that's waiting for it to, the one that's when first it's set to true and then it's waiting for false. And only the thread and its predecessor are looking at that memory location. So whatever cache coherency protocols are going on are only going on between two threads. Okay. With the TAS lock, all the threads that are trying to get that lock at once are all getting their caches invalidated, and they're all struggling to be the one that writes to that memory. Do you see that?
Right. Okay. And so then it's the non-uniform memory access that allows different processors to control different regions of memory and therefore not compete with each other. So
okay, so let me back you up there a minute. Okay, the CLH lock by itself, right, gets rid of minimizes the cache coherency problem, right? Because the CLH lock is going to reduce the contention for a Q node to two threads, right? From n threads, it goes down to two. But the CLH lock is constantly switching the Q node that it has, right? Because at the end of the routine, if you look at it, at the end, it does this thing where it sets my node to its predecessor's node, right? When it took that node used by the predecessor for the lock, and it makes it its own for the next time it wants a lock. So it's constantly switching which piece of memory that it's using to keep track of whether it has the lock. And the problem is, if you're on a NUMA machine, there's a possibility that memory that you've chosen to spin on may become remote memory. And it will be more difficult and time consuming to access. Yes, you're still going to have a cache coherency protocol on top of that, chances are. I mean, a cacherless NUMA machine is something we talk about in the slides, but I don't think that that's what anybody does anymore. But the point is, it might be dealing with memory across NUMA, so it could be slower. Now, the MCS, in addition to confining the memory access to a Q node to two threads like the CLH does, in addition to that, it keeps the same memory, right? Whenever it does, that it's spinning on, it keeps that same memory consistent. So it's not constantly switching the Q node like the CLH lock is. And because of that, it tends to perform better on NUMA machines. Does that make sense?
Right. Okay. So because each thread continues to hold the same object, the Q node, then that region of memory is then sort of allocated to just that thread, and it's not being. The only things that are moving around are the references between nodes and not actually the references to the nodes, I guess, for each thread.
Right. That the next field is changing, and who your predecessor is changing, but your node, your Q node, the my node, as it were, is staying the same.
Okay. Yeah, makes sense.
Derek, I think you're the most quiet person on this. Well, okay, so Derek and Brandon, I think you're both tied for the most quiet. Let's start with you, Derek. I'd like to hear you say something. Brandon, are you there?
Yes, I'm here.
So I'd like to hear some of your thoughts.
Well, I joined a few minutes late, so I was a little confused when I came in, but I don't know. I guess I'm just kind of confused on where to even ask a question, really.
Well, I like you to try and just identify something that's fuzzy in your mind, and something that maybe makes partial sense but not complete sense.
So this whole, sorry, I just missed the very beginning. So this whole chapter, is it just about comparing different sync or parallel operations that do the same thing?
This chapter is about locks. Okay, so chapter 2 was also about locks, as you recall. We had the Peterson lock, we had the filter lock, and we had the bakery lock. However, those locks were all locks that we constructed with atomic memory. And in the course of chapter 3 to 5, we learned that atomic memory isn't good enough, really, for building locks and that kind of and parallel control.
Right.
What we really need are atomic RMW instructions. And in the course of those chapters, we identified the compare and set as sort of the king of that. And so now that we've got atomic RMW instructions, we're going to see what kinds of locks we can build with those. Okay. And so the TAS lock was the first lock that we could build with that kind of instruction. All right, and it's pretty simple. What I do to get the lock is I call get and set, and I try to set I set the value to true. If I get a false back, then I drop out of the loop and I have the lock. And to unlock it, I write a false back. But to get the lock, what you do is you continually try to write the value true in there. Does it make sense?
Yeah, I think so.
All right. And so the problem that we identified with that is that calling get and set is going to invalidate the cache and is going to cause the whole cache subsystem on the machine to slow things down a lot. Everybody's going to get cache misses and invalidations, and they're all going to try to take control of the bus, and they're all going to try to get at memory location. And so we came up with this other idea, the TTAS lock. And the only thing that's different here is we call this get first, right? And this is just going to do a read. And if I do a read, I won't invalidate memory, but I might find out if I read it true, then I figure somebody else probably has the lock. And if somebody else has the lock, then I'm just gonna spin, right? I'm just gonna drop down to this yield here and let myself keep trying. On the other hand, if I actually get a false, then I'm going to try to call get and set to true, and try to actually take the lock. But as long as that thing is sitting there at true, I'm not going to bother. I'm not going to attempt memory to set memory and possibly cause a storm of invalidations. Does that make sense?
Yeah, so you're basically just doing some more preemptive checking to avoid some crazy situations.
Yeah. And then our next lock was the back off lock. And what we added, right, was we added some code to do some sleeping. If it looks like there's contention. So if we try to do this get and set and it fails, then we are going to guess that a bunch of threads are trying to get at that lock, and we're going to back off. And we're just going to go to sleep for some random amount of time in the hopes that we'll bypass that contention. And yeah, my min delay of 1 and max delay of 2. I was just playing around trying to figure out the right values for that. But almost everything I do winds up making, any kind of, all this back off stuff tends to just make this lock slower, at least for the test that I constructed. All right, and that takes us to the CLH lock, right? Which you've heard all the discussion about that, and the MCS lock, which are, well, I'm sorry, I skipped over the A lock, the Anderson lock. The Anderson lock, the CLH lock, and the MCS lock are all locks that make use of the RMW instruction, but they, in addition, they try to pay attention to the behavior of cache on the machine. And, this is a tricky game to play because the behavior of cache is hard-coded into the silicon, right? It's the way the machine is just wired. And it tries to do what it thinks is best for you, and then you try to make use of its logic for what it thinks is best. So it's kind of it's kind of like you're playing a strategy game against the CPU to try and make the cache work for you.
Mhm.
but you need to make the cache work for you. The basic problem is that on modern CPUs, the CPU is much faster than the memory. And so you need to take that into account if you're trying to achieve speed.
Right, that makes sense.
Derek, have you returned to us?
He sent a message saying that his device doesn't have a mic.
Yeah, I was able to get
Oh, I
that.
see.
I was able to get some headphones. I only have one question about the back off lock with
Yes.
the sleep method. So are you talking, when the current thread trying to acquire that lock, do we send that thread to sleep? Or the current thread trying to actually get to the lock while the other ones are trying to gain access as well? Do you go back to
Right.
that? Is that what that's doing?
Yes, it's saying that it's kind of like you want to get on a ride at Disney World, right? And you go and you take a look at the line and you see it's wrapped around the building and you say, I think I'll come back here in an hour and see if that line is any better.
Okay.
It's kind of like doing that.
Okay, so, and I heard you say, but so there's like no set time when you can put to sleep. You just kind of give it some random number to sleep and just check back later to see if it's available.
Yes.
Or not.
So the logic, the way the logic is set up in a back off lock, and I'm just going to change this to something, So the way the logic is set up is we have this limit field, which is the limit of the maximum time we're willing to delay. And then we pick a random time that's less than that limit. And then every time we have to go into this back off section, we increase the limit up until it reaches a maximum value. All right.
Okay.
And so that's just our strategy for how long we should wait for the queue to reduce in size.
Okay, that makes sense.
All right, I'm going to have to really work today to make sure I get all the grades done and I get the grade book in order, and then I have to submit your midterm grades. As you know, your midterm grades are not your final grades. And what they are, they're just a sort of a clue as to how well you're doing and whether you need to work harder or panic or whatever. And some of you do. It is very likely that I will say drop a lowest homework grade and or adjust thresholds for grades downward. So one of the things that I do at the end of the course, right, is I try not to fail anybody by 1/10 of a point, right? Fail isn't the right term. So suppose you're on an AB, A minus B plus boundary, right? And suppose you miss that boundary by let's say 1/100th of a point. Okay. I will probably adjust that grade down to catch you, because I just don't like to see anyone miss something by that narrow a margin. Okay. So I will probably do a couple of things of that nature at the end. So that, all your grades are kind of solid and there's a little extra fairness baked in. Does that make sense?
Mhm.
Yeah.
So it may, but I'm not going to fuss with that for the midterm. So if you miss it by 1/100th of a point in the midterm, I'm not going to try to adjust it to make up for that, because the midterm isn't a permanent grade. It's just a little signal to you guys. So you can sort of mentally adjust your grade, if you will, if you come close to a percentage barrier. Also, this is a good time. If I've got anything wrong in terms of your grades, I really need to see it. You really need you to tell me, what problems there are.
Are we allowed to talk about the midterm now, or?
Yes, if you have a question about the midterm, please raise it.
Yeah, the only thing I've noticed was the last Amdahl's law problem. I rounded to like 2 or 3 points like the previous one, but that one, the answer was like 8 points. And so I wasn't sure if that was going to be considered correct or not.
Well, I can look at your particular answer. I think I said in the question that it should be rounded to 3 decimal places.
Right, but the answer to one of the last ones, it said it was like 8 decimal places. I had the answer, but it wasn't the same exact number. Like it was like 3 decimal places versus 6 or something.
Okay, I will have to check what's going on there because I thought I had set them all to 3 decimal places tolerance.
I might be wrong, but that's just one of the thoughts I remember having after I took it.
There was also a problem that some people had with the execution diagrams. They didn't, a couple of people were confused because their screens weren't wide enough and they didn't realize that they needed to widen them, and the execution diagrams didn't display right on a narrow screen. I don't know if anybody here had a problem with that, but I will definitely take that sort of issue into account if you had a problem with it.
Yeah, I had that
Actually,
problem.
I had yeah, me too. I had the full size window, but it didn't seem to change the picture at all.
It worked
Right,
if
so
it worked if you copy and pasted it. Like I copy and pasted into Notepad, and then it came out
Well,
correct.
it will also work if you just hit Control minus and make your text smaller. I guess everybody has smaller displays than I do. Anyway, so I may do something about that question because it seemed to be a problem that a lot of people had, and only one person asked me about it during the exam. I gave you my phone number for a reason, right? I gave you guys my phone number so that you could call me if something didn't make sense, but for whatever reason, people didn't do that. Okay. Any other questions about the exam? All right. That's it for today then. And I will get you a homework assignment soon. I might even do another one of these quizzes. They seem to be working out rather well. Any final thoughts by anyone? All right. Thank you all for coming, and I will see you all next week.